Experiment 6, Potentiometric Fluoride Determination by Olivia Schroeder and Claire Schumack. Background. Fluoride is one of the most commonly occurring natural elements on Earth and is found in small concentrations in food that we eat daily. Some of the food with higher concentrations of fluoride are ground chicken, ground beef, black and green tea, and shellfish. Another way that fluoride finds its way into our food supply is based on the utensils and cookware that we use to prepare the food that we eat, both at home and in public. It has been determined that the use of Teflon cookware has resulted in an increase of the fluoride concentration in the food that is cooked in it. Another presence of fluoride that instead occurs artificially is the fluoridation of the tap water supply that is supplied to homes and communities around the U.S. Since we received the Good to Go from the World Health Organization back in the 1950s to add fluoride to tap water in an attempt to create a preventative barrier and decrease the rate of enamel decay in teeth, many other countries have followed our lead. The artificial addition of fluoride anions to our tap water has since become a controversial topic, partly because there has never been any actual known deficiencies of fluoride in humans, and because we do not know exactly how safe it is to be consuming tap water pumped full of fluoride ions. It is commonly believed that the introduction of fluoride into our tap water has only led to positive effects on our health, and therefore decreased the rate of enamel decay in the communities that it exists in. But this idea has since become challenged, leading to some countries and counties abandoning the idea overall. Currently, there are only 8 countries in the world that account for 50% of the fluoridization of the overall entire water supply. The reason that fluoride is added to our tap water is because that it decreases the rate of enamel decay. It has been found that toothpastes that do not contain fluoride are not effective at reducing the decay of enamel, so it is necessary to use a toothpaste containing some amount of fluoride to ensure that you are taking proper care of your teeth.
In this experiment, a solid-state ion selective electrode was used to determine the concentration of fluoride in tap water and toothpaste solutions. The purpose of using this instrument was to find the concentration of fluoride ions in both tap water and toothpaste. In addition to the ISE, a total ionic strength adjustment buffer, TSAB, was used to account for the unknowns and standards being different strengths. It is important to understand the amount of fluoride ions in tap water and toothpaste because we do not want to overconsume fluoride or not receive enough to maintain healthy teeth. Consuming too much fluoride can cause kidney toxicity, gastrointestinal problems like ulcers and inflammation of the stomach lining, skeletal fluorosis, and IQ deficits in children when consuming too much fluoride during pregnancy. Also, consuming too little fluoride can lead to tooth decay and weak, brittle bones. Our main goal of this experiment was to determine the amount of fluoride in tap water and toothpaste solutions by creating a calibration curve, then using the equation given by this curve to determine the concentration of fluoride ions present in each solution using the potential difference value from the ion selective electrode.
In this experiment, we used the total ionic strength adjustment buffer, otherwise known as TSAB, to account for the differences in ions of each solution. TSAB was used because it contains acetic acid and NaOH, and it maintains a pH of 5.5. It's composed of these elements, so it contains a constant pH. And this is important because at low pHs, some of the F- in the solution would form complexes with H, causing the electrode to measure less F-. And also at a pH of 5.5, it's low enough that there will not be interference from the existence of OH- ions. Another thing that comes with TSAB is the high concentration of NaCl, which keeps all of our samples and standards at a high constant ionic strength and keeps the activity constant for all of the individual solutions the same. Since there's such a large amount of NaCl and TSAB, the ionic strength of all the solutions is all relatively high, but they're high in equal strengths. So they hold them at the same ionic concentration, and this eliminates the effect of different ion concentrations of each solution and like what we may not know. Maintaining the activity constant for all the solutions at the same value is important because the potential difference determined by the ion selective electrode is not determined by the concentration of ions in the solution, but is determined by the activity of these ions. A constant activity constant using TSAB for each solution was important because the concentration of ions in all our solutions differed so greatly, and activity coefficients are dependent on ionic strength. If there were large differences in the activity constants of each solution, which there would be if we had not used TSAB, then we would not have been able to make realistic comparisons between the solutions of toothpaste and tap water because we were not completely sure of the ionic compositions and therefore strengths in both of these solutions. Another reason why TSAB was used was because of the presence of sodium citrate in it, and this can create complexes with ions that can exist in solutions such as aluminum 3+ and iron 3 that would otherwise become complex with F and interfere with the analysis.
The ion selective electrode was used in our The ion selective electrode is not based on redox processes. The membrane separating the inner and outer solutions is a hydrophobic organic polymer saturated with hydrophobic ion exchange. In the membrane, there is a ligand that will bind with the ion of interest, and in this case, it is the F- ion. Only a small amount of the fluoride is in the free form in the membrane because most of it is bound to the ligand. There is also a hydrophobic anion, R+, to balance charge. The analyte F- is in the filling solution, and the sample outside, and is also in the membrane. Because there is only a small amount of F- in the membrane that wants to move out into the aqueous solution, because there is a more favorable solvated by the water than by the organic solution in the membrane, but the hydrophobic anion R+ cannot diffuse into water. So this small amount of F- goes into the analyte solution because then the charge balance with the R+ holds it back. This slight separation of R+ and F- at the membrane solution interface causes the potential difference. Since the membrane contacts both inner and outer solution, there are two potentials. The potential on the inner is maintained as a constant because the filling solution keeps a constant composition. The more F- there is in the solution outside the membrane, the less of a driving force there is for the F- to diffuse into that solution, and the less there is a charge separation at the interface.
Step 1 of our procedure was to create an external calibration curve of fluoride standard solutions. And we did this using an 100 parts per million F- ion solution to create 6 different concentrated solutions ranging from 0.25 to 5.5 parts per million using the formula M1V1 equals M2V2. We calculated the volume of fluoride standard stock to add to each of these solutions to obtain our desired concentrations for our calibration curve, and then we used a micropipette to add this volume of F- standard solution to each of our 25 milliliter volumetric flasks. We used half of this volume, so 12.5 milliliters of TSAB in each of our solutions to control the ion activity, making half of the final volume TSAB. After the addition of TSAB, the solutions were then diluted to the 25 milliliter mark and distilled with distilled water and mixed. A calibration curve of the various concentrated standard solutions was plotted with the log of the concentration of F- versus the potential difference reading of the sample. The log of the concentration was used because the relationship between potential energy difference and the concentration of the solution is a log function of the concentration, as seen in this equation at 25 degrees Celsius. Step 2 of our procedure was to create the toothpaste and tap water solutions of unknown fluoride concentration to be analyzed using the electrode. The toothpaste solution was created by combining 0.225 grams of Colgate toothpaste with 50 milliliters of T-Sab in a beaker, heating it to a boil for 2 minutes, and then allowing it to cool to room temperature. When it had cooled, it was transferred to an 100 milliliter volumetric flask and diluted with 50 milliliters of distilled water to the line, and then mixed. This solution was diluted using distilled water because distilled water contains a negligible amount of ions that would be able to interfere with the activity and therefore the reading of the potential of our solution. 0.225 grams of toothpaste was used because it was determined that based on a 0.24% sodium fluoride concentration of the toothpaste solution, the concentration of fluoride in the distilled toothpaste solution would fall within our range of our calibration curve of 0.25 to 5.5 parts per million of fluoride. The tap water solution was created by mixing 15 milliliters of tap water with 15 milliliters of T-Sab and mixing it. Both the toothpaste and tap water solutions were divided into 10 milliliter portions to be analyzed using the fluoride ion selective electrode, and the F- of the tap water and toothpaste were calculated using the calibration curve created from the fluoride standard solutions in step 1. The calibration curve of the fluoride standard solutions created using the 100 part per million F- standard solution was made using the log of the concentration of the fluoride solutions and their respective measured potential differences. The concentration of fluoride in the sample solutions of tap water and toothpaste was then calculated by plugging in the measured potential difference of that solution into the equation of the calibration curve, y equals negative 58.524 x plus 67.153 for y, and then solving for x, or the concentration of standard, which would be F-. The fluoride concentration of the toothpaste solution using the calibration curve was calculated to be 2.689 parts per million, and the fluoride concentration of the tap water solution was calculated to be 0.7236 parts per million. Both of these concentrations of fluoride that had been determined using the calibration curve then had to be verified by calculating a percent spike recovery on both of them.
Even though T-Sab was used in this experiment to standardize the activity coefficients for each solution, a spike recovery was still done to test for matrix effects. T-Sab does help address some of the issues that activity creates, but does not solve all of them. Due to this, a spike recovery was performed to test for matrix effects. If matrix effects were present and our spike recovery did not fall in the range of 95 to 105%, then a standard addition must be performed to correct the matrix effects. The amount of solution used for our spike was determined by comparing the measured potential difference of the toothpaste solution to the values of concentrated fluoride solutions gave to us. Our desired C added is 50% of the 3.0 ppm, so we needed a 1.5 ppm spike. This amount of stock solution needed to create the spike was calculated to be 0.015 microliters. The calculations for C spike and C unspike were calculated by using the calculations for C spike and C unspike were calculated using the calibration curve equation by plugging in the potential difference determined from the ion selective electrode for y and solving for x. The calculation for C added was calculating by solving for V2 in the C1 V1 equals C2 V2 equation using the concentration of the stock solution, amount of stock used, and the amount of sample used. This was done for both the toothpaste and the tap water solutions. The percent spike recovery was performed to test for matrix effects and verify that our data was usable. Our percent spike for the tap water solution was good, that's why it gets a happy face next to it. However, the spike recovery for the toothpaste solution was not good and gets an upside down smiley face because that means we have to do a long standard addition calculation.
Because of the spike recovery percent calculation to be 132% for the toothpaste solution, we had to perform a long potentiometric standard addition on it. And the math for this potentiometric standard addition is different than that of like a normal standard addition because the activity of the ions in the solution have to be accounted for. And the reason that a normal standard solution could not be computed is because of these ions in the solution and like the other ions that we don't know about, there could be more potential matrix effects that we are not accounting for. The potentiometric standard addition plot has a y-axis of V naught plus V standard times 10 to the power of E2 minus E1 divided by S. V naught was the amount or the volume of the initial toothpaste sample tested before it was spiked or added with like any of the standard addition. And then E1 was the measured potential of that solution without any of the standard yet. V standard was the corresponding volume of the fluoride standard solution that had been added up to that point of the addition. And E2 was the measured potential difference of that respective solution at that point, containing that amount of volume. The S used was the slope of the calibration curve created using the fluoride standard concentration solutions. And this slope was used because it is a calibration curve that responds specifically to the fluorine ions in solutions. The standard addition completed on the toothpaste solution consisted of 6 additions of 15 microliters of 100 parts per million fluoride standard solution to the original toothpaste solution of 10 milliliters. This made each addition increase the volume of the original solution by 15 microliters. And the potential difference of the solution was measured using the ion selective electrode after each addition of 15 microliter sample to the toothpaste solution.
Using the concentration of sample determined by plugging in 0 for y in the equation of the calibration curve, we found the amount of grams of fluoride in 100 milliliters of toothpaste solution. This was then converted to grams of NaF in our sample and divided by the total amount of toothpaste used to get the amount of NaF in toothpaste. This value was then compared to the percent weight of the sodium fluoride in toothpaste claimed by Colgate, and we found there to be an 18.6% less NaF in toothpaste.
The percent composition of the active ingredient in toothpaste, sodium fluoride, was determined to be 19.52% in the solid concentration of toothpaste, not the toothpaste sample solution. This percent is close in proximity to the claimed percent volume of sodium fluoride in Colgate toothpaste to be 0.24%. The calculated percent error between the manufacturer claimed 0.24% and the experimental value of 0.196% was calculated to be 18.67% error, meaning that the value that we determined of sodium fluoride in our toothpaste solution is relatively close to the claimed value. So, yeah. Also, the tap water solution contained overall less concentration than the toothpaste solution. The educational purposes of this lab to learn how an ion selective electrode works to measure the activity of one specific ion in solutions and why TSAB is used in potentiometry were achieved. Potential differences develop in solutions because of the amount of fluoride already present in the electrode that is displaced when the electrode becomes immersed in a sample solution. So the amount of fluoride displaced is determined by the concentration of fluoride in this tested solution. Hence, a lower potential difference for the toothpaste solution and a higher for the tapped water solution. There was much less of a potential difference created when the electrode was placed in the toothpaste solution of higher concentration because the concentration of fluoride in the solution was already so high. That's compared to the tap water solution that had a very high potential reading because so much of the fluoride in the electrode rushed out because the concentration of fluoride in the tap water was so low compared to the toothpaste. The complicated process of a potentiometric standard addition was also learned and how to calculate it, showing us that you have to account for the activity of different ions in a solution, even if you use TSAB to deter those effects. One of the errors that could have been encountered in this experiment was the fluoride ion selective electrode not being filled enough throughout measuring our samples, and over time losing its filling solution of KCl. And it has to be filled to just below the top of the electrode at all times. And throughout the measurements, we noticed that it needed to be refilled, and so at some points, it was less than at other points, meaning that this could potentially create a difference in our ratings that we wouldn't really know about or be able to really account for. Another issue that we encountered was that in between the additions of the standard addition on the toothpaste solution, the electrode should not have been removed from the solution and rinsed of the sample. One potential source of error that could have been sourced from the removal of the electrode and it being rinsed with distilled water in between additions, is that some of the volume of the solution could have potentially been lost in between these additions because it was removed from the solution and rinsed. The way that this could have been fixed is by taking the electrode out of the solution, quickly adding the 15 microliters of standard, stirring it to mix, and then immediately placing the electrode back into the solution, making sure that all of the solution that was on the electrode gets back into that the original sample. This would ensure that none of the sample had a chance of escaping in between additions and would maintain the volume of each subsequent addition. A final source of error in this lab could have been the mix-up of the caps of the toothpaste and tap water solution during the standard addition. This error was coupled with the removal of the electrode during the toothpaste solution standard addition in between 15 microliter additions of fluoride standard solution, and it would have resulted in the transfer of some of the fluoride in the toothpaste solution being transferred into the tap water solution. The fluoride concentration of the toothpaste solution was much higher than that of the tap water, and so the concentrations of the solution present on the inside of the cap of the toothpaste would probably be enough to increase the amount of fluoride in tap water during the standard addition. And we decided to perform a standard addition on both solutions before we calculated a spike recovery of either. And because of this, we alternated back and forth between the fluoride and the tap water, going back and forth between the solutions, and we rinsed and blotted the electrode in between every addition. And in this case, something that could improve the experiment in this case would be the solutions undergoing completely different standard additions. Maybe even they could be done by different group members, so they were completely separate and weren't mixed up at all, and each person could focus on it separately. And then this would ensure that the most precise data possible for our standard addition curve would be used, and that even more accurate concentration of NaF would be calculated. Another correction that could be made to better this lab would to have spiked the tap water solution with a different spike that was used to spike the toothpaste solution. And this is because the measured potential of the tap water solution was much higher than that of the toothpaste solution, meaning that the concentration of fluoride in the tap water solution was just much lower. So if we had compared this higher potential of the tap water solution to the calibration curve, or the values of the calibration curve, as we did with the toothpaste solution, the spike of the tap water solution would have been a much smaller concentration than the 1.5 parts per million that we actually used. The 1.5 parts per million correlated with the toothpaste solution, and since the toothpaste solution had a much higher concentration of fluoride, it was incorrect for Dr. Gosher to advise us to use the same concentration for the spike for both, and next time we won't listen to her. We were not adding a realistic amount of fluoride standard to the original sample of tap water because the actual concentration of fluoride in the tap water solution was so low, and fixing this mistake would alter the results of our spike recovery for the tap water and actually might have resulted in another dreaded potentiometric calculation. So yeah, that's it.